Hey, welcome back to Artificial Intelligence 1. I'm Mr. Wong, and this is Lecture 1.1, entitled Goal-Based Search Agents and Their Environments. This is a follow-up to the last video, which was an introduction to artificial intelligence, and here we're starting to dive into the idea of intelligent agents. Let's recap a little bit. We left off last time with defining what intelligent or rational agents were. So this was our first diagram. We said that an intelligent agent exists in an environment, perhaps like a room, and it has sensors that are able to perceive things about the environment. So it receives percepts or observations, and the agent also has effectors or actuators because they can perform actions on the environment, thus affecting the environment, and the cycle continues. They receive more percepts, they do more actions. But we found that this wasn't really enough to make a satisfying definition of intelligence. And really what we cared about in the end was how we got from the percepts to the actions. What was mapping what our sensors perceived to what our actuators decided to do. And this here we called our model. We drew it again to be a little more clear. Our sensors and our actuators and an environment, but we said that our intelligent agent, for the purposes of this class, was going to be a problem-solving agent. So that necessitated a problem in the environment. At least for now. We'll maybe work with stuff in the future that don't have such clearly defined problems. But for now, we may have a very clear problem, such as how to get to the door. And of course, a problem means we're looking for a solution. How do we get to that door? How do we open it? How do we go through it without tripping over the entrance or bumping into the door frame on our way out? And so how we get from the problem to the solution is what we really are trying to do with the model. And so problem to solution, the model is composed of problem representation, search for the solution, and knowledge, which is the most vague part, but perhaps the most interesting part as well, and permeates the whole issue. So last time, we stopped right here, and I kind of skated over the fact that I had mentioned that we sometimes call these rational agents rather than intelligent agents. And I didn't really go on to elaborate what rational meant in this context. So let's talk about rationality. What is a rational agent? Well, we use the word rational a fair bit in everyday conversation, and we often use it to talk to one another about what we do or what we are thinking. And so here's a simple definition. Let's say that a rational agent is one that does the right thing, or we might say one that thinks about and comes to the decision on the right thing to do. Now, this definition is simple, and I like it because it's simple, and it points out something that is key to rationality. Rationality is about making choices. Now, whether you go through and actually do those choices, the actions that are associated with those choices, that's perhaps another question. But rationality is at least about making the choices that we have to make. Let's do a slightly more complicated definition. What do you think of this one? A rational agent is one that acts so as to achieve the best outcome. Okay, so once again, we have rationality about making choices in this definition, but it's a little more than that. It's about achieving some outcome and doing so with some measure of goodness, that we want the best outcome, and not just a good one, but optimal in some sense of performance. So rationality is about making choices for best performance. Okay, so this is also a good definition because it's not much longer, and it gives us direction as to what these choices are about. It's just not making choices, it's making choices with a goal in mind. But I'm going to add a little more to this definition. It's not complete. So, a rational agent is one that acts so as to achieve the best outcome, or when there is uncertainty, the best expected outcome. So, this adds a few words that make us realize there's another element to rationality. It's not just about making choices for performance, but has to do those choices in light of what it knows or doesn't know. So Rationality is about making choices for performance given knowledge or lack thereof. You can't expect someone to make the best choice without knowing certain things. And if they don't know certain things or do know certain things, you may expect more or less of them. A human example might be your friend calling you at 1 a.m. and says, hey, let's go buy some ice cream. Now, you, given your knowledge, because it's 1 a.m., this is not a good choice. If your performance measure for yourself is, well, this is going to make me lose sleep, this is going to make me tired for the next day, I don't really want to have sugar at this time of the night, it's not good for my health. Given what you know, this is not an optimal decision. However, perhaps your friend knows something that you don't. Maybe he knows that ice cream is on sale for 10 cents a gallon, and that going now is, in the long run, a much better idea than waiting till the next morning, even, because they're going to correct that mistake in the system at the supermarket. So, again, rationality depends upon what you know. So, I like these two definitions. They're short and they're sweet, especially the second one is short but still captures a lot. But I'm going to give you a slightly more technical definition. It's a little longer, but let's keep these three things in mind: choices, performance, and knowledge. So here's the definition. For each possible percept sequence, a rational agent should select an action that is expected to maximize its performance measure, given the evidence provided by the percept sequence and whatever built-in knowledge the agent has. Alright, that definitely was a little more technical sounding, but if we look closely, we'll see the exact same elements as the other definitions. It's all about selecting an action. It's about making choices. And it's to maximize its performance measure. That phrase, performance measure, is one that comes up a lot. Depending on what you're going for is what you define a performance measure on. Maybe your action's supposed to make something fast, or maybe it's supposed to make something very, very robust. It might be a long-term performance measure, it might be a short-term performance measure. Nonetheless, there's some quantifiable way we measure performance, and we're aiming to maximize it by our actions. And lastly, the knowledge component. There's a whole lot of stuff in here. For each possible percept sequence, since our agent sees over time, potentially, the idea is its knowledge has a lot to do with what it's perceived through its sensors. And hopefully it remembers what it's seen before, and it strings all those things together into useful knowledge. It has some sense of expectation, some ability to figure out what probably is best in the future, even if it doesn't know now. And the evidence provided by the percept sequence goes back to what we talked about earlier. Built-in knowledge is also a part of it. What the agent already knows about the environment, the problem itself, things that maybe it had before the percept sequence, that stuff is relevant to whether or not it's being rational as well. In case I get accused of plagiarism, I just want to say that all three of these definitions we just read came from the textbook by Russell and Norvig. It's called Artificial Intelligence, A Modern Approach. It's on its third edition, and I highly recommend this textbook. It's not cheap, but it is about as close as you get to a comprehensive treatment of this field of AI. So, not requiring it for this course, but I am recommending it for this course and onwards as a great reference. Okay, so let's return to our little diagram. With our new definition, added to the fact that it's a problem-solving agent, but he's rational, so he makes choices for performance maximization given knowledge that it has. And this is going to dovetail perfectly with what we said our model is composed of: problem representation, search, and knowledge. So, look at those things side by side. Our model of intelligence is made up of these three things, and our rationality component is made up of these three things. Well, you can tell already that knowledge is in both of them, so there's a great deal of overlap already. And choices and problem representation have a lot to do with each other, and the performance measure and search do too. But I guess rather than just saying that that's the case, I'm I'm going to map that out for you. We're going to focus first, though, on problem representation. That's going to be the main thrust of this lecture, and it's what I hope you start chewing on and taking away most out of the next 10, 20 minutes or so. And all three of these things that comprise rationality are involved in our problem representation. So let's do an example intelligent agent. This is a little device you might recognize. Let's call our Roomba, let's give him a name. Ronnie sounds like a good one. And he lives in a very simple environment. It's a 3x3 tiled room. And this tiled room occasionally gets dirty. Sometimes there's dirt on the different tiles. Ronnie's equipped with a number of sensors. He's got a camera that allows him to see the room and also the tile underneath of him, and bumpers that allow him to know that he's up against a wall, and so he can't go into the wall. He's got some wheels that allow him to move, and he's also got a device that allows him to suck up dirt and clean the area that's below him. So Ronnie, at any point in time, sits on one of these tiles in the room. And this is the beginning of using our knowledge about the environment to represent our problem. So we might say that this room at any point in time is in a given state. And we can describe that state with a few factors. One being, where is Ronnie in the room? Right now he's in the second column and the second row. And also the dirtiness of each tile. We might say that the upper left corner, the right tile, and the bottom tile are all dirty right now, and everything else is clean. And what we just said fully describes our state of the environment. There might be some initial state where we know we start off when we turn Ronnie on. So let's just say this is our initial state, with Ronnie in the middle and the 3 dirt. And a state space. So the state space is all the possible states that this environment could be in. So if we look at this, there are 9 possible places Ronnie could be, and there are 9 possible spots for dirt to be. So each of the 9 possible spots could be dirty or not dirty, so that allows us to maybe work out the math and find that our state space is roughly 2 to the 9 times 9 for the number of places that Ronnie could be. If you work that out, I think that comes out somewhere between 4,000 and 5,000. So it's a fairly large state space. Surprisingly so, for where it is. Here's another spot that Ronnie could be at. Here's another state that it could be. All 3 of those things we just flashed through are different states. And that's only 3 of all the possible states in the state space. Now, states are great, but we care about the choices that Ronnie is making. That's an important part of the problem representation. So we call those the actions that Ronnie has available, and there's a limited number of them. He can move in 4 different directions, and he can also clean the spot that he's on. And what happens when he does these actions is defined by a transition model. So we say that a transition model tells you, given the state that you're in and the action that you perform, what is the next state that results. So, and we might start developing this transition model by going through each state and determining what its neighbor states are. All the resulting states from all the possible actions in a state. So let's take the initial state we've got here on the right and figure out its neighbor states. If he goes north, he gets this state. West, south, or east, he gets all those states. Now what happens if he cleans? Well, if he cleans, nothing really happens. He just ends up where he is. In fact, we could probably draw another arrow for cleaning, but it would just loop right back to the same state because he's cleaned an already clean tile. So we can either build this into the transition model and say that the state plus the action clean results back in the same state, or we could simply say that that action is invalid in that state. So that can also be a part of the representation, saying which actions are valid in which states. Let's take a look at the rightmost state there, and let's try and do this again as an exercise. Let's go through and find all the neighbor states of this one, thus expanding our transition model, making it a little closer to complete. So from here, we could also go north, west, and south, but we can't go east. We might say that this is, we could also draw an arrow back to the same state because it would just bump against the wall and stay there. Or in this case, we might say that it's invalid, especially if such a state not only, perhaps Ronnie, if we take away his bumpers, cares a little more about hitting the wall, and it's not as benign to just go east and slam into the wall. So we might say that's an invalid state because we just can't afford to do it. But he can, in this state, cause a new state to arise if he cleans. So, again, there are still 4 neighbor states, or distinct new neighbor states for this particular state. And so we would go on, keep doing this with our states and available actions in each state to eventually enumerate the entire transition model. Of course, we said that there were 4,000 to 5,000 possible states in just this simple environment. So doing this by hand can be kind of messy, but thankfully, in a lot of cases, our states are factored into particular properties, and we know what the actions do to the various properties, so the transition model can be a little easier to enumerate in a few simple rules rather than going through every single possible state. Still, sometimes it's helpful to enumerate all the states, or at least a small subset of them, to understand what's really going on. Okay, so lots so far. We've created our problem representation by having states and all the possible states, which makes up its space, an initial state, and we listed also its actions and transition model, which will tell us the neighboring states of every state. And so this uses knowledge about our environment and choices, tells us about our choices that we have available to us. So a lot of components of our rationality are becoming salient at this point. But what's left? Well, we didn't define performance at all. What's our performance measure? We've got an environment, and intuitively, we probably already know what Ronnie should be doing to prove himself useful, but we haven't really defined it at all. We've just said, this is the way things are, and this is what happens if you do that, or that. So we're going to define what's called a goal state, or there might be multiple of them. A goal state is simply what state of the environment we want to end up at. So for Ronnie, as you might guess, the goal state would be having all of the dirt cleaned up. Now, this is one such goal state, but there are in fact 8 others, because we don't care where Ronnie is at the end. We just care that all the dirt's cleaned up. So there are 9 different goal states. Now, that means this is a particular kind of agent. This is a goal-based agent. His entire purpose is to achieve that goal state. And if he does, well, good for him. His life is complete, or at least his task is complete for the moment until he's given another task, another goal. So in order to get to that goal state, though, we need to define something else. So define a path as a series of states and actions. So here's an example path. We start here, and we can perform an action moving to the east, and that results in another state. And here's another path, or another part of the path. He does a clean action, and that results in the third state. And so we might say that this path is 2 actions long or 3 states long. Some people define it in one or the other way. But that's essentially what a path is, just a series of states and actions that lead from one to the next. And so what we're looking for, our solution, is a path from the initial state to a goal state. So we're looking for some series of actions and states in between that get from here to perhaps here. And this process of looking for the goal state, trying to find a solution that gets us from the initial to the goal, is called search. Now, search is the focus of where our performance measure has to do with. So now it's a goal-based search agent, and now we can finally ask questions about, well, how did it perform? And it might be a measure having to do with the solution itself. How good is the solution? And it might be a performance measure having to do with the process of search. How quickly did we find it? Did we find it using a lot of resources? Did it take a lot of memory or something like that? So performance measure is something that we're going to talk a lot more about in the future But for now, you can start imagining what kind of things we might care about in terms of performance. For Ronnie, maybe we care about how far he had to travel, or how quickly he was able to get the dirt cleaned up. You can imagine all sorts of ways that we might measure the performance. But we'll talk more about that next time. So, to recap, we've talked about knowledge and choices, and briefly, performance. And it might seem like, well, we're pretty good. We're sitting pretty. We've got a really great definition here, and we can get going, actually, on the next lecture at this point. But I'm going to say don't close out the video yet. There's just a little bit more I want to talk about. I want to revisit the knowledge that we asserted so quickly about the states of our environment. We assumed a number of things, even if you don't realize it. So I want to go back and examine some of those assumptions, both about our agent and the environment that he's in. So Ronnie, we said, had a camera, and that allowed him to see the whole room and also what was below him. But perhaps his camera is a really nice one. Maybe it's an upgraded model. Maybe our friend has a cheaper version of Ronnie, and his Ronnie can not see that far. In fact, he's only capable of really seeing the spot below him, right? We might say that our Ronnie is fully observable, or for to Ronnie, the state space is fully observable. And he can see everything about the state that he's in. Whereas our friend's Ronnie is only partially observable. He can't see the whole room that he's in. And of course, if we took ours and put him into a very, very large room, or even put him outside and said clean, we probably have to admit that at some point, Ronnie can't truly be the environment that Ronnie's in can't truly be fully observable. He can only see so far. So, in our case, we're lucky, but if we do have a partially observable environment, there's ways to deal with it. We take the sensors and the percepts that are coming in, and based on what we see, Ronnie will develop belief states, a guess, a list of all the possible ways that the world could actually be, and work from there. But thankfully, that's not the case for our little example. The second is deterministic versus stochastic or probabilistic environments. So in our environment, we said that if Ronnie moves or if Ronnie cleans, well, there's only one possible way that it could turn out. We're certain that that action will lead to this particular state. But what if there's some probability involved? What if when he moves, there's a 90% chance of successfully doing it without any hitch, but every now and then, with 10% chance, he'll leave behind a little dirt. He's not perfect, and he doesn't know for sure what could come out. So this would be a stochastic or a probabilistic environment. Now this is more difficult, but there's a way to kind of deal with it. We would say that instead of saying our transition model says state plus action results in another state, we give instead a distribution of states. We say the probability of ending up in any number of these states. And that allows us to calculate expectation of performance, even if we can't figure out exactly what's going to happen. We have some ideas, some best guess of where he's going to end up. Related to this is a third possibility, non-determinism, where we don't even have the probabilities associated with the transitions. We just know that it could be one or the other. And this is similar. We just have to calculate all the possible things that could end up happening and plan based off of that. The third property is the fact that this environment has to do with a series of actions, a sequence of them. In some environments, it doesn't matter so much whether or not he does the order of actions in any particular way or not. We call those episodic environments, whereas when they do matter, one action leading to the next can't be switched around, then we would say that's a sequential environment. Episodic environments often, the actions all just happen at once. And you just say, okay, I've decided on these things, and because the order doesn't matter, we just get back to you all at one time. Here's the fourth assumption that we made, which is that right now, we said that the state doesn't change while Ronnie's waiting around and deciding what he's going to do next. But in most real-life situations, other things could happen. Dust builds up and more dirt accumulates on the floor as Ronnie waits there deciding what to do. We would say that that's a dynamic environment as opposed to our static environment where nothing will happen in between waiting for the deciding what to do. So a dynamics action means that or a dynamic environment means that the state might actually change before you choose an action and do it. This is more difficult to deal with, and this means that we should probably focus on finding a good action quickly before the state changes and we have to start all over again. And of course, what might happen, what might be causing that dynamic environment might be the fact that there are other things in this environment. So maybe, if we're lucky, there's a second Roomba helping out, cleaning out on his own, and that's very helpful, though we don't know exactly what he'll do, perhaps. Or maybe there's some more nefarious agent in the environment who's working maybe against us or doesn't care what we're doing, but unfortunately has his own goals. So maybe like a dog who's kicking up dirt. And so we would specify that our agent before was in a single agent environment, but now there's multiple agents acting in this environment. They might be cooperative or competitive. You can guess between the extra Roomba and the dog which is which. But those definitely make things more complicated and contribute to the dynamic flavor of our environment. So let's review all the things we just went over. We're talking about properties of the environment, and here are some of the possibilities we mentioned. Observability, deterministicness, sequential or episodic, dynamic or static, and how many agents there are in the environment. And we said ours, as we had originally defined it, was fully observable, deterministic, sequential, static, and single agent. And as you might have guessed, with the exception of sequential and episodic, the ones we've landed on for all the other ones are the easier versions of the possibilities. And you might be saying, Mr. Wong, I thought we were going to create some robust agents in this class, and you will, but you have to walk before you can run. And it turns out that most of the more difficult options of these properties have their analog in the easier one. As we mentioned, partial observability, for example, does belief states, which effectively just converts things into a fully observable problem. Similar goes for stochastic and probabilistic environments. They just model things as multiple deterministic environments with certain probabilities, and so on and so forth. We'll touch on most of these options in the course and how we deal with them, but we'll start with this particular realm of properties in order to get a good grasp on what agents are supposed to do. And so these are actually all additional components of the knowledge that we have about our environment. And our agent uses these to its full extent. It exploits the fact that the environment is this simple or that complicated in order to do its best at being rational. So, in conclusion, this is where we ended up. We've got a really good approach to problem representation for a lot of problems, and it involves knowledge and choices, and we also said all the definitions of the things that we need to know for how we're going to approach searching and hopefully meet our performance measure or maximize our performance measure in that. We're going to go into more depth about how we define those performance measures and how we actually conduct the search to meet those performance measures in the future. But for now, we're going to practice a little bit with some of the problem representation part and applying that framework of states, actions, transition model to a few examples. So don't forget your homework. There's a reading response with this video and also some pre-class exercises that go slightly beyond what we talked about here, but will be a good start for what we discuss in class. So I'll see you then. Thanks for listening and watching.